morning, everyone. We are starting our colloquium. Today, we are very pleased to have Ben-Zvi as our speaker. Just to introduce David briefly, he's currently based at the University of Texas at Austin, but he received his PhD from Harvard, and he was supervised by Professor Edward Frankel. David's research interests combine representation theory, mathematical physics, and algebraic geometry. And today he will talk about his work in which ideas originating in quantum field theory are applied to a problem in number theory. David, the floor is yours.
Thanks so much. It's a great pleasure to be here or there. And yeah, so I'm very glad for the invitation, and I'm excited to tell you about the story about electromagnetic duality. So I'm going to be giving, as Sergey said, a perspective on some problems in number theory, specifically the problem of understanding periods of automorphic forms, inspired by ideas in physics, specifically the theory of boundary theories for supersymmetric gauge theory. And everything I'm going to be talking about is joint work with Yiannis Sakellaridis at Johns Hopkins and Akshay Venkatesh at the Institute. Okay, so let's start with a little bit about arithmetic and physics. So when we talk about the theory of automorphic forms, the theory of automorphic forms can be presented, often is thought about as a problem in quantum mechanics. It's a very specific problem in quantum mechanics. It's a problem of quantum mechanics on the class of arithmetic locally symmetric spaces. So what does that mean? The famous example pictured here, we think about the modular group SL2Z acting on the upper half space, which I'm going to describe as the quotient SL2R by SO2. So we look at the upper half space, and we study quantum mechanics on the quotient, if you'd like, on this fundamental domain for the modular group. So in other words, we're going to study the Hilbert space of L2 functions on H mod gamma, and Hamiltonian, which is the hyperbolic Laplacian acting on this Hilbert space. We might study its spectral decomposition and various properties. There's variants of this where instead of L2 functions, we might study things like L2 differential forms and various twisted things, but let me kind of sweep that under the rug. So this is kind of the classical setting for the theory of modular forms is as part of a problem in quantum mechanics on the upper half space. Now, more generally, if we have a reductive algebraic group, so think GLN, symplectic groups, orthogonal groups, any of your favorite Lie groups, you can study a similar problem. You can similarly set up an arithmetic locally symmetric space. For example, you can take the real points of your group, mod out by a maximal compact subgroup, and you get a symmetric space, your analog of the upper half space. And then you can mod out by an arithmetic by a lattice, a discrete subgroup, like the integer points of your group. I'm going to use this kind of notation where it just called this the box G as a kind of shorthand notation for this arithmetic locally symmetric space associated to G. Okay, so this is the basic quantum mechanical setting, and there's a lot of interesting work on this from a point of view of quantum mechanics. What I'd like to emphasize is some special features of this problem that are very different from kind of general quantum mechanics. It's a very, very, very special problem that has a lot of interesting features. Let me highlight some of the features that are special to this setting. Perhaps the most important, the most characteristic features of this arithmetic quantum mechanics is the existence of Hecke operators. So let me not define the Hecke operators, but say that this quantum problem has a huge commuting algebra of symmetries, many, many operators commuting with the Hamiltonian. So it's some kind of quantum integrable system. So this algebra is called the Hecke algebra, the collection of Hecke operators. And these are the classical operators that Hecke considered. For every prime number p, there's an operator TP acting on L2 of upper half space mod gamma. And these operators all commute. And so we can study so there's a lot of redundancy, if you like, in the quantum mechanics. We should study the joint spectral decomposition of all these commuting operators. There's a version of this for any of our group G, rather than just sort of one operator at each prime. The operators at each prime are labeled by representations of a complex or a compact Lie group that's dual, called the Langlands dual group, dual to our original group G. So look at finite dimensional representations of this compact Lie group or complex Lie group, and those label Hecke operators. So there's a big collection of operators labeled by representation theoretic data, and they all commute. So that's already something very special about this quantum mechanical problem. Okay, let me just pause for a second to point out that I'm not so used to giving slide talks. And so I might tend to go extra fast. So please interrupt me and ask questions. There's also a lot of caffeine in the system, so I'll try to slow down. Okay, so all right, so this is our general setup. Now, what else is special? We have this algebra of Hecke operators, but there's a lot more. So another thing you might have already asked when I started talking about modular forms, usually when people talk about modular forms, you don't look at modular forms for the full group SL2Z, you look at a congruent subgroup. So in other words, you take a positive integer n, and you might make some conditions on your SL2Z, on your integral matrices. You may make conditions that these matrices satisfy some congruences mod n. So if you like, you're fixing a bunch of primes, the divisors of n, and for each of those primes, you're making some conditions on the reduction of your matrix mod n. So really, we have a collection of problems, not just the upper half space mod SL2Z, but a collection labeled by congruence conditions at primes. So we should think about this whole family together rather than just this original problem. Okay, now, I'm very happy to share the slides afterwards. Yeah. So now that's another problem. What else can we vary? There's something else that's maybe less explicit, another variable in this situation that's less explicit, which is there's a number field involved. Well, it appeared through the appearance of Z as the ring of integers of the rational numbers. So secretly, this quantum mechanical problem also depends on the choice of a number field. Here, in other words, a finite extension of the rational numbers. So we could vary this finite extension of the rational numbers, and you can write a space, in the case of SL2, there's a variant of the upper half space. There's several ways to set it up. You could take your field, tensor it with the real numbers. Now you get a real Lie group, and you can mod out by a maximal compact subgroup. So now we have a locally symmetric space like before, and there's a natural lattice there, which is SL2 over the ring of integers in your number field. So for example, if you start with an imaginary quadratic field, this gives you, rather than a quotient of the upper half space, this gives you a quotient of hyperbolic 3 space. And so you have this collection of arithmetic quotients of hyperbolic 3 space. And again, what I want to say is I want to think about all of these collections as we vary the number field, as we vary the congruent subgroup. These are all part of the same problem. There's close interactions between them. So it's really a family of quantum mechanical problems with this extra symmetry, the Hecke operators, and with these extra variables. Okay, and maybe the most exciting special feature is the Langlands correspondence. So the Langlands correspondence very, very coarsely says that these automorphic forms, these eigenfunctions for this quantum system, are labeled by representations of Galois groups of your number field. That's a kind of very coarse way of saying it. In other words, it's saying that there's a relation between this geometry of this arithmetic locally symmetric space and a problem which you can think of as a problem in group theory or a problem in algebraic geometry. We'll study the collection of representations of this group, this profinite group, the Galois group, into this Langlands dual complex group. So these are the kind of Galois representations that are relevant. So there's a duality that relates the theory of automorphic forms with the theory of Galois representations. From the point of view of quantum mechanics, you could say that this Galois side, which I'll call the spectral side, kind of solves the quantum integrable system. In other words, what do I mean by solving the quantum integrable system? It simultaneously diagonalizes all these Hecke operators. So the collection of all these Hecke operators on automorphic forms get diagonalized. They become multiplication operators by certain functions. For every representation of this complex group, remember that this data, these representational complex group with the same data that label the Hecke operators. For the same data, there's some multiplication operators. These representations will label the eigenvalues of Hecke operators appearing on automorphic forms. That's sort of what the Langlands correspondence says very coarsely. So you can solve this quantum integrable system and describe its spectrum in terms of this dual data. Yes, was there a question?
Yeah, can I ask about this K, the choice of K earlier? So I mean, normally this is like some kind of maximal compact, but isn't there some choice involved there as well? For
Yeah,
G?
so I'm going to kind of sweep that under the rug of, so there, that's kind of plays the role for the infinite primes with Archimedean primes for the real places that the congruent subgroup conditions. So secretly there was a choice at every prime P, and the choice at infinity is somehow maybe more obvious in the way I wrote the notation. There's a different way to write it, this Adelic point of view, where it makes all the points look on equal footing. The way we wrote it, we emphasize the real points and then K, so K kind of pops out at you. You could ask the same question at every P, and there are these choices that are these congruent subgroups. Okay, so this is kind of the setup. We have a quantum mechanic problem, or really it comes in a big family of quantum mechanic problems with a huge algebra of symmetry and this very interesting duality. And we'd like to kind of use physics to gain some insight into this problem, but quantum mechanics per se is sort of too poor a receptacle for this. There's too much structure here that's not there in a kind of a generic problem of quantum mechanics. It's a very, very special situation. What I'd like to promote today is there's a much better paradigm for this. Rather than think about this as a problem in quantum mechanics, we're going to try to formulate this as a problem in four-dimensional quantum field theory. Now, this is going to be less precise than the statement you can literally do quantum mechanics on the upper half space. This will not literally be a quantum field theory, but it'll have what I would like to promote is the idea that all the structure, all this huge amount of structure that I just discussed, that we see in the number theory problem, is a structure that you already see in four-dimensional quantum field theory, and that's a really better way of encapsulating what's going on in the number theory. That's kind of the message I'd like to present today. So it's going so this may be what you might call an arithmetic quantum field theory. So it'll be a very close analog of structures in quantum field theory. That's the paradigm I want to take. To make it more precise, I think there's a lot of physicists around in the audience. There's a particular four-dimensional quantum field theory that we're going to use as the model. And that's four-dimensional maximally supersymmetric Yang-Mills theory with a gauge group, which is the compact, maximal compact of our original group G. And it's a particular topological field theory. So what I'm going to be talking about today is topological quantum field theory. And it's a particular topological twist, which I'll call the A-type twist. And I think my slides are sort of slid off the bottom. This is called the GL twist with parameter psi equals 0 for the experts in the audience. But in any case, there's a particular four-dimensional quantum field theory that I want to use as the model for this number theory problem. And this is very heavily influenced by the work of Kapustin-Witten, who interpreted the geometric Langlands program, which is some kind of geometric, already a translated version of the original Langlands program. They interpreted it in terms of electromagnetic duality for exactly maximally supersymmetric Yang-Mills. So they kind of gave us the prototype, and we're going to try to apply their paradigm to think about the questions in number theory. Okay. Any questions so far? Okay. So how does this work? So I claim that there was this huge variety of structure in my number theoretic problem, and I want to line that up with a huge variety of structure that you see in four-dimensional quantum field theory. So what's the analogy? So there's my slides remind me if I have all my references at the bottom. They keep sliding off. So there's a famous dictionary that people call the Arithmetic Topology Dictionary, or sometimes called the Knots and Primes Dictionary. And in this dictionary, we're supposed to think of a number field, or maybe better, think of the ring of integers of that number field, or spectrum, as an analog of a three manifold. So when we were varying number fields before, I want us to think that we're actually varying three manifolds. So that's where the topology comes in, where three dimensions comes in. In this dictionary, the prime numbers, so primes in this ring of integers, are analogs of knots in the three manifold. So this is a dictionary that goes back to work of Mazur and Artin Verdier, and there's a long history of it. It's become Morishida, Kapranov, Resnikov, a lot of people have developed this. In the last few years, it's really been promoted by Min-Young Kim, who's been developing the idea of arithmetic version of Chern-Simons theory, arithmetic quantum field theory. So what I'd like to do is somehow analogous. Instead of arithmetic Chern-Simons theory, I'm going to try to do arithmetic n equals 4 Yang-Mills in the same spirit. Okay. But at least this is our basic dictionary, that when you see a number field, I want you to think 3-manifold. When you see a prime, I want you to think not. Now, I said 4-dimensional quantum field theory, whereas 4, here I have 3 manifolds. And the idea is that I'm going to be thinking about the Hilbert space. I'm going to be thinking about the Hamiltonian formalism. I'll be thinking about a 3-manifold, which is a fixed time slice. So in other words, in a 4-dimensional quantum field theory, we attach a Hilbert space to a fixed time slice. That Hilbert space is very roughly the quantum mechanics on some space of fields for fixed time. So here we're roughly doing quantum mechanics on the space of connections, gauge fields, connections. There might be some auxiliary scalar fields, other fields, but we're doing quantum mechanics on some space of fields on a fixed time slice. And to that we attach a Hilbert space, and that Hilbert space is playing the analog of this L2 of this arithmetic locally symmetric space that we had before. So the quantum mechanics problem now I want to think of as being part of a 4-dimensional field theory. It's a Hilbert space at fixed time. Okay. So this is quite vague, but you can make it more precise, a better ansatz. I'm not going to try to capture quantum mechanics or quantum field theory in its full glory. If you like, I'm going to kill time. I'm going to kill time dependence. So I'm only going to study the topologically twisted version. So rather than doing honest full quantum mechanics, studying the whole spectrum of the Laplacian, I'm going to be studying topological quantum mechanics. So if you like, replace L2 functions by L2 differential forms, and then pass to cohomology. So rather than studying L2 functions on arithmetic locally symmetric spaces, we'll study cohomology of locally symmetric spaces, also known as cohomology of arithmetic groups. So that loses something, but it keeps most of what we want. The whole theory of classical modular forms can be expressed purely in this cohomological setting. So the part that we're going to be most interested in for number theory, we're going to think of as being part of a problem in topological quantum mechanics, supersymmetric quantum mechanics, if you prefer. And again, the idea is that rather than studying a full quantum field theory, we're going to study a topological quantum field theory. So that means that we're going to take this giant Hilbert space and we're going to pass the cohomologies of some operator, some BRST operator. So in the particular topological version we're doing, this means that rather than studying the full Riemannian geometry of the space of connections, we're just going to be studying the topology of the space of connections. That's the topological twist we're looking at. So that's going to make things, the physics, infinitely simpler, but it still lines up with the things we're interested in number theory. Okay. So my ansatz is going to be thinking about topological 4-dimensional field theory. So M, my manifold, is just a manifold. I don't need to think about metrics. Is that okay so far?
Oh, excuse me.
Yeah.
Just ask you mentioned the supersymmetric quantum mechanics. I just want to make sure you have a description of a Hilbert space, right? And then the spectrum of the fermionic states and bosonic states are degenerate.
Yes.
And there is a unitary description for the whole system. Is that right? Which means the system is unitary. But I'm just not sure whether the maybe the earlier motivated the super young Mills with this topological twist are unitary, as far as I understand. So how is one go from a presumably non-unitary theory to the unitary supersymmetric quantum mechanics? Or maybe I missed something.
I guess I would say that maybe plead to complete ignorance about unitarity. I mean, we're doing Euclidean quantum field theory, and we're doing and we're only going to study the topological. So the only parts that I really feel of this dictionary that I feel are pretty well founded are think about the purely the topological sector. And so I'm not going to have anything to say about anything like the unitary structure. So we're just going to talk about this topologically twisted n equals 4 super young Mills. And we're going to ignore any structure. So again, notice here, I'm just passing to cohomology of some space. I'm forgetting about L2. Unitarity is very important in the number theory too, but I won't have anything to say about it, and I'm not sure how it fits. So that's a very interesting question, but can't really comment on it. Okay.
Thanks.
Yeah. So right, and again, I should say I'm using the in response to the question and comments. I'm using the word Hilbert space in this coarse way that people use it in topological field theory. Hilbert space here just really means a complex vector space. So we're passing to cohomology of some some Q operator of some space of field, and it's just going to be a vector space. There's not going to be any inner product around. Okay. So you might complain again that I've thrown away a lot of what makes quantum mechanics interesting. I'm ignoring the unitarity, I'm ignoring time evolution. So I've thrown away a lot of the structure, but we're still going to keep a lot of interesting things. So first of all, what we've done so far is only explained at least the variable, which is the number field. The variable in our problem before, which is dependence on number field, I want to make an analogy with, which is the variable, which is I can have a vector space attached to any 3 manifold. Okay, that's not a whole lot of structure so far. What makes things much richer, and this is kind of one of the main insights of Kapustin and Witten, was that the Hecke operators, the most important part of this number theoretic problem, our vector space had a big commuting action of operators, and well, so does the Hilbert spaces in gauge theory also have these. So there's the Hecke operators for each prime. So again, remember that a prime we're supposed to think of as the analog of a knot. And in this gauge theory, there's one-dimensional defects. There's monopole operators. So we can study the 4-dimensional theory with inserting magnetic monopoles, the 't Hooft operators, along some knots. So here's my picture. I have my manifold M, and I have M times time. And at halftime, if you will, I'm inserting a monopole singularity, inserting a 't Hooft operator around some loop in M. And this picture is in the quantum field theory defines an operator on the vector space attached to M. So we get an operator, and it's labeled by, well, first of all, it's labeled by the knot. That's analog of the labeling by the prime. But it's also the data that you need to specify in a 't Hooft loop ends up being exactly the same data, a representation of this dual group. That's exactly the singularity data that specifies a magnetic monopole and 't Hooft monopole in this theory. So we have a collection of operators, and these loop operators commute with each other. So we get a big commuting family of operators on this vector space. So we get, this is a well-known source of quantum integrability in topological field theory. You have a lot of commuting operators in topological field theory. So here we're looking at these 't Hooft loop operators. So we have a vector space will come with this big commuting algebra of symmetries. So that's already telling us that's sort of the most important aspect of the number theory that we're seeing appearing naturally in the physics. There's other features that maybe I don't want to spend too much time on them, but for example, we had this variation where we could change the ramification. Or we had not a single setup, we had a setup for each congruent subgroup. So we had a whole family of quantum mechanical problems, and that data is also captured nicely in the physics. These are by 2-dimensional defects or surface operators in the physics. So given again, and my picture is the same knot, but now I'm doing something else. I'm considering it as a defect. I'm thinking of the Hilbert spaces of the theory with a singularity along this knot times time. So this is my surface here. This is my surface defect. So when you study the field theory in the presence of these surface defects, you get a collection of vector spaces labeled by all these data, which defects you put in. So that matches exactly now and you can make this more precise and really label the surface defects in the physics. The labelings match up in a nice way with the labels of the ramification data in number theory. Okay. So we've seen some of the kind of salient features of the arithmetic problem appearing, having analogs in the physics. But the most important feature, if you'd like, the most exciting aspect in number theory is the Langlands program. And again, this is somehow the point of Kapustin-Witten's work, is that Langlands correspondence has a beautiful analog in physics, which is electromagnetic duality. So just like Maxwell theory, supersymmetric Yang-Mills theory has a symmetry that switches electricity and magnetism. This is this Hamiltonian S duality. So, and there's a version of that for this twisted n=4 super Yang-Mills. So this particular gauge theory we're talking about has a symmetry that exchanges the group G with the group G dual. So there are two Lie groups around. I can think of them as both being UN. But for example, if I take SU2 as G, then G dual will be SO3. So the groups are different on the two sides of the duality. And it also changed the topological twists we're dealing with. So in this particular version, what electromagnetic duality does, it exchanges this 4D A model with something we call a 4D model. So the letters are supposed to are in reference to mirror symmetry. This is in some sense a 4D analog of mirror symmetry. So on one side, we're studying the topology of these spaces of connections on three manifolds. On the other side, we're not going to study the entire space of all connections. We're going to just study flat connections. In other words, representations of the fundamental group of my three manifold. Look at the space of representation of the fundamental group into this Langlands dual group. And those are given by some algebraic equations. They form an algebraic variety, and we can kind of do algebraic geometry, complex algebraic geometry on this space. So the way this electromagnetic duality works in this topological twisted theory, the topology of spaces of connections is exchanged with the algebraic geometry of these spaces of monodromy representations, local systems. So that's what's left of electromagnetic duality after topologically twisting. And Kapustin-Witten explained that this realizes the Langlands correspondence. So how does that work? So here's the big chart. So we have two sides here of this duality. In number theory, we'd call one the automorphic side, the other the spectral side or Galois side. In physics, we're going to have the two sides of the duality, which I would call magnetic and electric, or the A side and the B side. Now, you might complain in the physics, the way the physics is presented, it starts out symmetric. The two sides look very similar, except that the groups have been exchanged. But you're studying the same kind of quantum field theory on both sides. The way the number theory was presented, the two sides look completely different. And this is actually a feature, not a bug here. One of the ways in which we'd like to use physics to gain insights, this is similar to what happens in geometric lengths, is that the two sides actually are symmetric. And you can use that symmetry to try to make predictions, to understand what's going on better. Well, in the number theory, the symmetry has been completely broken. But here in particular, the symmetry between electricity and magnetism has been broken. On the A side, we only have magnetic phenomena. On the B side, we only have electric phenomena. And again, the A side means we're studying topology either of spaces of connections or of these arithmetic locally symmetric spaces. So that's the automorphic forms, or these A-twisted Yang-Mills theory. That's studying topology. On the B side, we're doing algebraic geometry. In physics, we're studying flat connections. In number theory, we're algebraic geometry of these varieties of Galois representations. So that's the flavor of the two sides, the A side and the B side, just like in mirror symmetry. Now, what else happens? We have these loop operators, these operators that are the Heck operators, or in physics, they're tough loop operators, and they get exchanged with much simpler operators, Wilson operators, or these trace of Frobenius operators. So these are complicated. On the automorphic side, these are complicated convolution operators. And these sides are, or if you like, disorder operators, and these are multiplication or order operators. Okay, this is not. Okay. Multiplication operators. So that's the theory of the one-dimensional defects in the physics. There's also theory of two-dimensional defects, these solenoids. In the theory of automorphic form, they appeared in this as having congruent subgroups. On the dual side, they correspond to thinking of flat connections, which are allowed to have singularities, allowed to have monodromia and some subspace along and around a knot. You're allowed, okay, around your knot. Okay, so what I was trying to emphasize is we have this very, very rich dictionary where you can match up all these phenomena in the number theory. Really, all the features that appear in the number theory could line up to structures that appear very natural in the physics. We're asking just the most natural questions to ask about a four-dimensional field theory. What are the operators of various dimensions, for example? What I'd like to talk about today, what my work is about with Sakellaridis and Venkatesh, you can think of in this way, that we're going to extend this dictionary another row. We're going to study what happens when you study three-dimensional defects in the quantum field theory. So that's, or if you'd like, these appear as boundary conditions or maybe domain walls. We're going to think what happens when you study three-dimensional defects, and we're going to use that to interpret a problem in number theory, which is the relation between periods and L-functions. So that's kind of the message, is that the relation between periods and L-functions is something that can naturally appears in the physics as electromagnetic duality for boundary conditions. Okay, now I need to explain what periods are, what L-functions are, what that's all about. But maybe let's pause for a second for questions. Right. Yeah. So yeah. So what do I? So by A side. So yeah. So here we're in the A side. We're thinking about yeah. So if you'd like, there's two ways of thinking about what's going on the A side. I can think about it. I'm presenting it as topology of spaces of connections, or you can think about it as symplectic topology of spaces of Higgs bundles. So, for example, when you compactify an Riemann surface, you have the Hitchin space, which is a hyperkähler manifold, and you can study its symplectic topology of the Hitchin space. Hitchin space is roughly the cotangent bundle of the space of Yang-Mills connection on the surface. And so in general principle in Floer theory is that Floer theory of the cotangent bundle, the A model on a cotangent bundle has to do with the topology of a base, Morse theory on the base. So I'm suppressing the symplectic topology aspect by kind of polarizing, by think of only half the variables. So it's A side is symplectic topology of some cotangent bundles, or just ordinary topology of the base. Great. All right, so now let me go to our main topic. Again, we're going to ask there's a basic theme, which is that L functions in number theory can be often written as integrals. There's the integral representation of L functions as certain special integrals called periods, and that's what we'd like to understand using the physics. Okay, so what are periods? So the most famous period, classically, this is the Hecke period, maybe the first period, is I'm going to give you an automorphic form phi. Maybe I'll ask it to vanish at the cusps. So it's a function on the upper half plane, which is modular. And there's a basic measurement I could do. So period is going to be a basic measurement, a basic integral I can do for my automorphic form. And this is the Hecke period. I'm going to integrate, I'm going to do a Mellon transform. I'm going to integrate this period along this blue line here. So I'm take this vertical axis in the upper half space, and I'm going to take my form and integrate it maybe with some factor depending on S. Okay, so that's called the period. This integral of my form has the basic measurement of my form, and I'm calling it the T period because this blue axis that I'm writing is really the orbit of diagonal matrices. It's the orbit of a maximal torus inside of SL2R. That's the role of T. So really, I have this, if you like, something like an arithmetic locally symmetric space for T, which is not much to draw. It's just this vertical axis. I'm thinking of it inside of the space for G, and I'm just restricting my automorphic form and integrating. So that's the basic Hecke period. If you like, my picture also had a red axis, so I figured I should make some comment on it. This is called the constant term of the modular form, also known as the Eisenstein period. That's defined in a similar way. You can take your cusp form and, or not the cusp form, I guess, take a modular form and integrate it on a horizontal axis, and you get another interesting period. But let me focus on the blue period, the Hecke period. Okay. So now, what did Hecke do with this integral of a modular form? What Hecke showed is that you can identify this period up to some normalizing factor. You can identify this period with the L function of a cusp form. So I won't give the formula of the L function of a cusp form. You make a Dirichlet series out of the coefficients, but there's if you'd like, this could be, you could think about this as a definition of what the L function, this is a definition of what the L function of phi is. The L function of phi up to a factor is just this Hecke period, just this integral. Great. Now, why are we calling it an L function? Because L functions have a completely different manifestation on the other side of the Langlands correspondence. So if your cusp form happens to connect to some two-dimensional Galois representation, so we apply this magic dictionary of Langlands, or if you like, of Taylor-Wiles, and if you have a two-dimensional Galois representation, then the idea is that this L function attached to the cusp form will agree with the L function attached to a Galois representation. L function attached to a Galois representation is something given by this kind of formula. It's a product of inverses of determinants. And what determinants of what? You make an operator, you take the Frobenius operator at P, you apply the two-dimensional representation on it, you get a 2x2 matrix, you take its determinant. Okay. So this is a formula you can get out of a two-dimensional representation of Galois group using just its action on these Frobenius elements. So it's some very fancy characteristic polynomial. That's how you should think of it. Some big kind of characteristic polynomial built out of a two-dimensional Galois representation. So this is the key point for these L functions that we wrote you can think about them as coming from number theory, from the study of these Frobenius elements. They have this analytic interpretation. They have this integral representation, integral on this vertical axis. Okay. You can, let me not kind of bore you with all the details. You can do, there are many, many more periods you can write this way. You can do a lot of other integrals. For example, if I take a subgroup of G in general, you take your favorite Lie group G, you take a subgroup, you can try to define a period. You, by integrate, you take the local arithmetic locally symmetric space you build for H, and you think of that as a subspace of the arithmetic locally symmetric space for G, and you can take your forms and restrict them and integrate. So there's lots of natural integral measurements for your automorphic forms. Now, and in fact, writing H as a subgroup is neither necessary or sufficient. Really, what I want to emphasize is not thinking of H, but of thinking of the homogeneous space G mod H. You can rewrite this integral that we're writing, instead of as being about integrating on a subgroup, you can rewrite it as an integral transform, as an operator where you, yes, you can write an integral operator associated to a G space X. And it turns out to be neither necessary nor sufficient for this to be homogeneous. So the fact that X happened to be given to us as G mod H is not enough for this integral to be well behaved, to have good properties, and it's not necessary. So there are lots of interesting periods that don't have to do with homogeneous spaces, don't have to do with subgroups, but the ones that do that are good are not arbitrary. So this finiteness condition is known as the notion of the theory of spherical varieties. So spherical varieties, I think, are not as well known as they should be outside of representation theory, unlike toric varieties. But spherical varieties are the precise non-abelian analog of toric varieties. So think of a toric variety for a torus. Now imagine replacing T by non-abelian group. The natural class of the varieties that you get are the class of spherical varieties. So I've given here the definition. It's somehow not very helpful. It's kind of doesn't convey why this is an interesting notion, but at least you will recover the notion of toric. You want to have a variety where the Borel subgroup has finitely many orbits. That's the definition. Maybe a better thing to say is that this captures lots and lots and lots of interesting spaces in representation theory, somehow most of the spaces that appear. So for example, flag varieties, symmetric spaces appear. The group itself can be thought of as a spherical variety for the square of the group. There are many, many examples, but maybe the first example is just to think about toric varieties themselves. And what's the simplest toric variety? The simplest toric variety is the complex line with the action of C star. And Tate's thesis can be written in that way. So if you write the period associated to the affine line with the action of the multiplicative group, that period is exactly what Tate was studying. And this is how Tate wrote the functional equation for the Riemann zeta function, Dirichlet L series, and more. So that period doesn't fit into the paradigm of a subgroup. It's a homogeneous, the homogeneous space. It's the action of the multiplicative group acting the affine line. That's the Tate period. So there are many, many interesting examples of periods that appear throughout number theory, and they're labeled by these spherical varieties. Okay, so great. So there's a beautiful theory of these integrals that you can do, integrals of automorphic forms labeled, and the natural data that labels them are these spherical varieties. And there's a lot of them, and they're extremely important in number theory. They're important in number theory because basically all the good analytic properties that we know for L functions come when you can write an L function as a period. So the integral representation of L functions is one of the main tools one has for studying L functions. You take an L function that appeared in number theory, you write it as some period of an automorphic form. Writing it as an integral gives you things like functional equation and analytic continuation, kind of nice analytic properties. So this is kind of one of the main ways that we have of accessing L functions. That's great. But there's a basic problem. And the basic problem is that the data that label the two sides, the data that naturally labels L functions and the data that labels periods just don't match. So what are L functions? I didn't give you a general definition of L functions, but L function is the thing that's labeled by I have a representation of a Galois group into a Lie group, and I'm making some fancy characteristic polynomial by taking some characteristic polynomials of Frobenius elements. So what this representation does to Frobenius elements of Galois groups, and make some big product of these. Those are what L functions are in Galois theory. That's great, but the data that labels this is a representation of this dual group. on the other hand, the data that labeled periods was spherical varieties for G. So on one side, we have representations of the dual group. On the other hand, we have spherical varieties for G, and these data just don't line up at all. In many of the cases of interest, you can take your favorite L function and write it as in particular period, but there's no general kind of science to how this should be done. And that's what we'd like to address. Okay. All right, any questions? Okay, so now let me propose how we want to address this problem. And the idea is I want to address this problem as I advertise using quantum field theory, using boundary conditions in quantum field theory. This is what I'll call the relative Langlands duality. So before that, let me mention some of the work of Sakellaridis and Venkatesh. In their book, they study this theory of periods and they enrich it a lot. They expand it on the automorphic side. This global theory of periods, this is something that had to do with automorphic forms and number fields. There's a local version. You take your group G over a local field, something like the p-adic numbers or the real numbers, for example, and you might study a classical harmonic analysis problem. We have a G space X. So here X is my spherical variety on which G acts. So again, think of a toric variety. And you might study just L2 functions on X and ask, how does G act? Try to decompose this to understand these particular representations. So we have a source of interesting harmonic analysis problems for G, which is take X over this local field and understand the representation of G on that. Now, and they showed that this was very closely tied to this global theory of periods. They fit in a beautiful package, which is part of what's called the relative Langlands program. And what they also did is they showed that you can extract from this spherical variety, from this X, you can extract some data, some dual data, which is you can extract a subgroup of the dual group and a representation of the subgroup. You can squeeze some, basically by combinatorics of this spherical variety, just like combinatorics of toric varieties. You can squeeze out some data of a subgroup and a representation of the subgroup, and that these data, combinatorial data, control all the things you care about in this X relative Langlands program. So, for example, you can ask, when does this period of the automorphic form, when is it non-zero? That's a basic question you can ask. I give you a modular form, I take these integrals, is it going to be zero or not? That's controlled by this data. The local problem in the harmonic analysis, which representations appear when you study this particular space X? Which representations of G appear there? Or maybe a fancier version of that, what is the Plancherel measure? How do you decompose, spectrally decompose L2 of X under G? So these data are all controlled by this combinatorial data, which have a Langlands dual flavor, and that's kind of our starting point. Okay, so what our proposal is that this entire theory of periods and the theory of L functions naturally fit into a richer structure, which is the structure of a boundary theory, a boundary condition in the gauge theory. In other words, what is a boundary theory? Very coarsely, we're going to be studying quantum field theory with a local boundary condition on the fields. So the way, all I really want to extract from that is a local boundary condition gives you a state in the Hilbert space on any manifold M, or really gives an object of whatever you attach to. It's a local object. So any patch of space that you study, you can consider that patch. Here's my picture as I'm studying a patch of space across a time interval. And I'm putting this boundary condition on the other end. This is my given boundary condition. And this picture produces particular elements of what I might have attached to M. So particularly Hilbert space of M will have vector attached to this boundary theory. So it's a boundary theory gives a collection of data in the quantum field theory. On any manifold you might study your field theory, it gives you particular states there. And they all fit together in a very rich way. This is through locality. And whenever you have a duality, when you have an equivalence of field theories, it's going to have to identify boundary conditions in one theory, boundary conditions in the other. That's what a duality has to do. It identifies all the structure on both sides. So what we'd like to do is interpret periods and L functions as boundary conditions, as states are given by boundary conditions. So in this supersymmetric Yang-Mills theory, Galois and Witten studied these half BPS, these maximally supersymmetric boundary conditions in super Yang-Mills theory. And what they showed that they were roughly given by something geometric, by holomorphic Hamiltonian actions of your group G. The data to specify a boundary condition is essentially a G space, a holomorphic Hamiltonian action of G. So the way these appear is by these data are what allow you to write a three-dimensional supersymmetric sigma model that you can couple to the gauge theory. We don't need to worry about that. So that's roughly the geometric data that specifies boundary conditions. And what you deduce from this, what Galois saw from this, is that there's some kind of mysterious duality between Hamiltonian actions, holomorphic Hamiltonian actions of a group G, and holomorphic Hamiltonian actions of a Langlands dual group, because both of these are giving boundary conditions on the two sides of the correspondence. So this is something that's not at all obvious geometrically, how to relate Hamiltonian G spaces and Hamiltonian G dual spaces. But that's a prediction of electromagnetic duality. Okay. So how does that help us? What I'd like to do is translate our problem of periods into Hamiltonian G spaces, our problem of L functions into Hamiltonian G dual spaces, and then see the symmetry. Okay. So let me try to walk you through, how do I go from a period to something that looks like Hamiltonian space? So we started talking about periods. We said, let's take a subgroup H of my group G. So H is a subgroup of G. That's the data I started with, like the vertical axis I integrated on. It was the orbit of this H. Okay, and then we said, well, we don't actually need a subgroup. We really just need the homogeneous space X. We can form the homogeneous space G mod H. And then you could think, well, okay, that's a special case of a G variety. Let's forget that it was homogeneous. Let's just think about G variety. So I have here in probably invisible green, the finiteness conditions, the spherical, that I want these to be spherical. Let me not worry about the finiteness conditions. So we said, okay, you started by studying subgroups. Now let's talk about G varieties X. Now the next translation I want to do is replace X by its cotangent bundle. So rather than studying G varieties X, I want to study their cotangent bundle. Now, why is that a natural thing to do? That's very natural from the point of view of quantum mechanics. If I'm studying quantum mechanics on X, the classical phase space is the cotangent bundle. And in some sense, a lot of things in quantum mechanics are really micro-local. There are aspects about quantization of the cotangent bundle. And we've broken some of the symmetry by focusing on just position space rather than momentum space. And in fact, if you look back at Tate's proof of the functional equation for the zeta function, it is given by a Fourier transform on the affine line. And what that Fourier transform really is doing is going from a position space picture to a momentum space picture. And that's where the functional equation for zeta comes from. So really, even when Tate is talking about the affine line and this C star acting on it, he's somehow secretly thinking about its cotangent bundle in Fourier theory. So that's the next translation. I don't want to think about G varieties. I want to think about their cotangents. And their cotangents are Hamiltonian G varieties. They have an action of G that respects a symplectic structure and has a moment map that generates this action. So instead of thinking about cotangent bundles, and now let's drop being cotangent bundles, and let's just think about Hamiltonian G varieties. Okay. So again, my basic example is T star of G mod H. But by thinking about it as a Hamiltonian G space, for example, I get many more examples. I get more symmetries like Fourier transform, but I get many more examples. The most famous is the theta correspondence in number theory. There are many more examples of periods that can be described in terms of microlocally, described in terms of Hamiltonian G spaces than in terms of G spaces. This is one insight of Sakellaridis Venkatesh. So we're going to replace X by M. And so if you like the physics, I'm studying a sigma model into M, and this is exactly what Kapustin-Witten tells us appears as boundary conditions in gauge theory. Periods are relatively close to these boundary conditions. We've just had to replace our X by its cotangent bundle. And that's where our Hamiltonian spaces arise. What about the dual side? The dual side maybe looked pretty far from Hamiltonian G dual spaces, and that's kind of the main dictionary here. So let me just point out this characteristic polynomial thing. When we talk about 1 over a determinant of 1 minus, use the formula for a geometric series. What you're secretly doing, or one way to interpret what this 1 over determinant is, it's a trace. It's a graded trace, graded by T, graded trace on a symmetric algebra. That's the geometric series. So rather than studying a vector space V with a dual action, I'm studying the symmetric algebra V, which I could think of, if you like, as polynomial functions on the dual. And I'm just doing graded trace of this Frobenius operator on this ring of functions. So I want to get rid of this point of view. I want to think about functions, traces on symmetric algebras. So in other words, I'm going to replace the representation V by this variety V dual, which let me call it X check. So this is now a variety with a G check action. So I can rewrite the L function in terms of the data of this. It's just an affine space with this G check action. So now now you realize that you don't need to stick to representations. You can talk about G check varieties instead. You can attach L functions in this way to varieties using algebraic functions on them, using trace of Frobenius on functions on them. And now you can do the same trick. Now you can pass to its cotangent bundle. And now you have a Hamiltonian G dual variety. Now you have a symplectic variety with an action of this group, which is given by Hamiltonian vector fields. And now you're in physics, because now you can talk about the physics of maps into this Hamiltonian G space. That's the data that defines the boundary conditions in the physics. So now we've gotten into a boundary theory for this electric side of electromagnetic duality. So that's how I want to translate an L function into a boundary condition. So that's our basic dictionary. So okay, so then again, so what I've just to recap, we've taken both sides, both the period sides and the L function side, and we've rewritten them in terms of Hamiltonian actions of the two groups. And now, so now what we need to do is figure out how to match the two sides. And so the idea is that rather than trying to directly match period and L functions, I'm going to match boundary conditions, match Hamiltonian actions for G and G dual. And I want to just end with just a little bit of insight on how you actually might see this duality. One of the beautiful things in the physics is it lets you actually extract. This is one of the ideas from the topological field theory. You can actually extract the data of a Hamiltonian G dual space out of stuff on the automorphic side. You can build it, and you build it directly as some kind of moduli space of vacua or a Coulomb branch for this boundary theory. So we're going to take this boundary theory, and there's a procedure in the physics which is construct a moduli space of vacua for this theory. And the claim is that that will exactly produce for us. We do this on the A side. We start with our A side. We start on automorphic forms, but we're going to build out of it this data on the dual side. Okay. So how do you do that? Very roughly, I'm going to create an algebra and a module for it. The algebra is going to be given by line operators in the bulk theory, and the module is given by line operators on the boundary theory. I'll draw a picture in a second. And we have an operation of acting by line operators in the bulk, on line operators in the boundary. That'll give us a module. And then we'll kind of describe these spectra. If you like, take these algebras and take their spectrum. And that will produce for us this data. So that's the idea. So we're going to construct these spaces just out of the structure of defects in the field theory. Okay, so this is probably certainly too fast. So let me just end with, give you some math here. So the idea is that you can build a tensor category out of bulk line operators and a tensor category out of boundary line operators. So here, these are my bulk line operators. These are defects in the bulk of my space that my bulk has to do is this gauge theory associated with G. So I have these bunch of lines, and I can imagine colliding them. So you can imagine from this kind of slice point of view, it looks roughly like a pair of pants type picture. I guess I drew 3 points rather than 2, but that's supposed to remind you of a pair of pants. So that's a kind of multiplication of defects in the theory, and they form a commutative algebra because you can move these guys around each other. And then you can collide them with line defects. Maybe I can zoom in a little bit. You can collide these with line defects that lie in the boundary. Line defects and line boundary can still be collided with each other. They're less commutative, and they can be acted on by things in the bulk. So we've constructed an algebra, a commutative algebra, and a module for it. And the modules actually still has some commutative multiplication. And now you ask, what are all these things in the math? The bulk line operator, that's what had these 'T' line defects. And one of the basic things we know in the Langlands program is what is the structure of the algebra of 'T' line defects. It's given by a theorem called the geometric Satake correspondence. In any case, we know the algebra of the Hecke operators, or the 'T' operators, and they correspond to sheaves on the coadjoint quotient of the dual group. So we construct the coadjoint quotient of the dual group from bulk line operators. On the other hand, you can think of what are line operators on the boundary. There's some kind of sheaves on some loop space. Okay, I'm happy to go, let me not go into this in detail. I'm happy to elaborate in a second. but these produce the module. And so if you like, we see here these two spaces. I have the Hamiltonian space and its moment map. These appear just by studying the spectrum of line defects. So that's a kind of the main point of how we can build one side from the other. And so now, just to summarize, if you take all the combinatorial work of Sakellaridis and Venkatesh, it lets you give a precise prediction what this dual space should be. You could build it directly, there's a formula for it, out of the kind of combinatorial data built out of spherical variety. It wasn't clear, this formula doesn't make it clear that it's a Hamiltonian dual space, but you get that structure, that's our prediction, and you get out of this a whole bunch of conjectures. In local setting, global setting, geometric settings, a whole family of conjectures from the duality of field theories that tell you how the entire automorphic theory relative to M or X, like the study of periods and harmonic analysis, tells you exactly how it should fit, how it should be dual to the B side, the spectral theory, the theory of L-functions as algebraic geometry of this action. It gives you a series of precise conjectures that you can, in some cases, you can verify and give you some insight into how the two sides should match. And so let me conclude there. Thank you very much.
Thank you very much, David. Do we have any questions that have not been asked yet?
Yeah, let me. So you started with basically quantum mechanics on this quotient spaces, and but mostly you were, and then you passed to flat bundles on the space. And is there any precise relationship between eigenfunctions of the Laplacian and flat bundles and sections of flat bundles? Maybe it's possible to somehow expand those.
No, so I somehow from the point of view of like the dynamics of the physics, I've killed all the dynamics. So the Laplace, so I'm doing this topological quantum mechanics where I've made the Laplacian has been Q exact, and I'm passing to cohomology. So the Laplacian is acting by zero on the cohomology side. So the on the spectrum. So, but this is something you can see very nicely already just in Maxwell theory. You just study Maxwell theory, and you can make a twist. So, Maxwell theory on a three manifold, you have a Hilbert space, which is the L2 functions on space of all connections, G bundles with connections on your three manifold. And what you can do is you can pass to a cohomology of the space of connections. That's one topological twist you can do. Under electromagnetic duality, so that the cohomology, it just becomes a sum over a lattice, the lattice of magnetic fluxes. So that space has components labeled by H2 of your three manifolds, which are magnetic fluxes. And on the other side, in electromagnetic duality, the dual twist just picks out holomorphic functions on the space of flat connections. So there's a dual Q operator on the electric side, and it just picks out functions on that. So you have the torus of flat connections on your three manifold, flat U1 bundles, and functions on that torus exactly line up with cohomology with this function on the lattice. So this electromagnetic duality becomes something kind of silly, becomes just a Fourier series. On one side, you have the lattice of magnetic fluxes. The other side, you have the torus of electric fluxes. And those two are identified. So that's where the space of flat connections comes from. It's seeing a very small part of the physics. Likewise, on the automorphic side, I'm not seeing the whole richness of the space of connections. I'm just seeing its cohomology. And so that's kind of what's happening in general. The topological quantum field theory I'm doing is killing a lot of the information in the Young-Mills theory. I'm only remembering sort of some topological aspect. And the two sides, the way the duality works, the two sides I'm remembering different aspects. One side I'm really remembering topology, and the other side is like a B model. I'm remembering holomorphic geometry of some space of flat connections.
Well, yeah, I see that, but I mean, is there a way? Well, it's obviously outside of your talk, but is there a way to somehow use this topological functions, the flat connections, to maybe somehow express as a series the actual dynamical eigenfunctions? So there's nothing like that.
That's a great question. I have nothing to say. I'm sorry. That's a great question. In fact, I think it's in the relation so far between gauge theory and Langlands program that I'm aware of in Kapustin-Witten, it's all about the topological theory. And it would be really interesting, in quantum in the theory of automorphic forms, there's a lot of dynamics. There's a lot of study of eigenvalues of the Laplacian. It'd be interesting if you can gain any insight to that. Does this analogy even work? Does it break down? Is it only something that makes sense in the topological sector, or it'll be fascinating to see, but I have no insight at all.
Thank you.
Let's see, could I ask a question?
Sure.
Let's see, so in this extended topological quantum field theory, there are relations between defects of various different dimensions. So how is the structure reflected? You use a part of it, it seems, but what is the general structure, extended TQFT structure in your context?
I mean, I don't know how to summarize it. I mean, as you know, it's extremely rich. So
yes, that's right. So
what I know is that I think one of the amazing things that is from this Kapustin-Witten dictionary is that somehow every piece of structure in the Langlands program and in the physics in the topological field theory seems to line up. So all the phenomena that I know of in the physics line up with the phenomena. So you have interesting structure of surface defects. You have fusion of surface defects is something that plays an interesting role. You can think of, here I was looking at line operators on a boundary condition. You can study line operators living on surface defects. I mean, I don't know. There's a lot of rich representation theoretic structure to the collection of defects of all dimensions, form more and more commutative, less and less categorical things. So like local operators are very commutative. They form what's called the E4 algebra. Line operators are this E3 category. Surface operators are some version of a braided tensor 2 category. And all of these things act on each other, and they all act on boundary theories. Boundary theories are kind of the richest, where you see everything act, all the other ones act. So the way I think about that is that it's really that you're doing a kind of a Fourier transform, that you're starting with the A-side theory, and you have this very rich algebraic structure given by defects, and it's roughly some kind of big commutative algebra, and you're taking spectrum of this, and that's some version of describing a moduli space of vacua of the theory, and you're trying to write the A-side theory in terms of this moduli space of vacua description. That's what the algebra of defects gives you the geometry of the moduli space of vacua, and you can think of that as giving a very good approximation to the dual theory. It doesn't completely determine the dual theory, but the duality is very roughly, I go from the A side and I construct the B side, I construct the mirror as some kind of spectrum of algebra of defects. So Langlands duality, so I guess the answer to your question is Langlands duality. The whole Langlands correspondence is in some sense spectral decomposition of the automorphic theory under defects.
Mm-hmm. So is it fair to say that not all extended TQFT structures has been explored so far? Do you expect more than that? Certainly more than what you talked about today, or?
I mean, certainly that's my that's been my agenda for a while. It's trying to. I mean, if I knew a particularly good question, I would explore it. But I think that's certainly the case. That's our work is trying to explore. So boundary conditions in this theory are relatively new. Haven't been explored in the math until relatively recently. There's a series of works in that, but I think there's probably a lot more to say. And I'm sure there's a lot more to say. There are a lot of basic questions. For example, in Kapustin-Witten, they never even consider what the Hilbert space on a 3-manifold is.
Mm-hmm.
It's a very basic question in the TFT. And the Langlands program hasn't really dealt with 3-manifolds directly very much. So I think there is a lot of interesting math out there to be expected.
Let us stop the recording now, but please feel free to stay on the channel. Thank you very much, David, again.
Thank you.
Yeah, nice talk. Thank you.
Thank you.
Yeah, can I ask one more question?